Okay, you hear the sound? Okay, very good. Welcome back, everybody, to this morning's primary main talk, and then after coffee, we'll have a more informal discussion. But we'll begin for now with Bing Guo, who will ask the question, are there echoes of gravitational waves?
Oh, good morning, everyone. Before my talk, I would like to thank all the organizers, Nick, Joseph, and Andrew, and all the people here contribute to this. Maxine. For this great meeting. So today I will talk about something a little simple about the echoes of gravitational waves based on recent work with Samir. So before going into the detail, I will mention the main results of this work. So the main problem in the gravitational echo is because the gravity is so weak, so it's very hard to build a model that you can reflect significant fraction of the gravitational wave. So we try to understand this. We find a model that can do this. And the second thing is, in the most of the research, they neglect the back reaction. So we consider this back reaction, and the result is we are not be able to see these echoes. Okay, so this is the outline. So I will introduce the idea of the echo and the model for the finite temperature fuzzballs, even though we do not have much of them. And the discussion, the refraction of the gravitational wave, and then the formation of new trap surface. If you have any questions and comments, please tell me. It should be very simple, so you can. So this is a picture of black hole, and this dashed line is the horizon. If you look at the wave equation near the black hole, so you should put the ingoing boundary condition, and the horizon as place r equals to 2gm. And suppose we can find the microstate of the black hole, and we replace this black hole by a exotic compact object. So it's very compact. So we studied a very compact case, and the surface of this compact object is at 2gm times 1 plus epsilon. So epsilon is very small. Maybe there's suppose there's some quantum effects. So there's some possibility we can put the reflecting boundary condition on the surface of this compact object. So that's the usual way people do the gravitational echoes. So I took 2 pictures from Cardoso and Pauni. And so in this picture, this surface is the the surface of the compact object, and we put the reflecting boundary condition here. And this is the photon sphere. So if we start with a wave here, it goes inside to the black hole, black hole or the compact object. Because we put the reflecting boundary condition here, it will be reflected and moving outside. And at the photon sphere, we have a potential barrier, and part of the wave will go inside again. So we'll get, and at this point, this part of the wave will go to infinity. So you will have wave reflecting in this 2 boundaries, and you get lots of gravitational wave. And the time difference between 2 nearby echoes is determined by the traveling time from this surface to the photon sphere. And this time is this values. It increases with the, if epsilon is very small, this time is a little bit large. So for a solar mass black hole, if you put the cutoff at the Planck scale, so you will get this about 50 million seconds. So suppose this is the main part of the gravitational wave coalescence of 2 black holes, and you will get a clean signal after the rain down, much after the rain down, and the separation between 2 different echoes are very large, so you can get a clean signal here, but not too far from the main signal, so you can still detect, it's possible to detect them. Any question? Okay. Now let's look at the radiation. So this is a picture of a black hole, and we know the particles are virtual near the horizon. And because the slice is stretched, so when the particle rail reach the point delta r at approximately m, this virtual particle becomes real particle. But if you look at a compact object, there's no stretching effect. So the particle should be emitted directly from the surface. And the surface is s away from the proper distance away from the horizon. So since this particle must be real from beginning and emitted directly from the ECO surface. So that's the difference. For the black hole, you will not see real particle near the horizon, close to the horizon, but for ECO, you will see real particle close to the horizon, the ECO surface. Let's look at the properties of this radiation from the ECO, because if this compact object describe all the microstates, it has to have very large entropy. So that means the surface is very rough. So the emission is almost isotropic in all directions. So it cannot go directly outward. It should go other directions. And if you look at the local energy, if you want to recover the Hawking temperature at far away, so this is the Hawking temperature, the energy of the particle at the infinity. So due to this blue shift factor, you will get a large energy close to the ECO surface. It's 1 over s. S is the distance of the ECO surface to proper distance to the horizon. It's not Hawking. If you want to recover the emission from far away, then if you want to recover the same temperature for this object.
Just a comment, maybe I understood it to be the temperature of the body which replaces the black hole, which you're setting by hand equal to the Hawking temperature value for that Schwarzschild mass.
You get the temperature at the surface of the sun, and then you have Coleman's law that covers the temperature anywhere else.
We want this object to be the microstate ensemble of microstates of black holes. So we want to recover the same temperature at infinity.
I think what he's doing is he's simply saying, look, let's take a black hole, replace it by something, but let's keep its Hawking temperature, let's keep all its sort of physical thermodynamic properties, and now let's put a reflective surface on it. I think that's what he's saying.
Oh, yes.
So he wants to have Hawking temperature, and he wants this surface with an epsilon of the horizon. And now he's looking at what the reflecting surface does, but I think you're assuming that there's Hawking temperature already there and the Hawking pair production somehow through this reflective surface, right?
We want to recover the radiation, but it's generated from the surface, not from the pair creation.
Oh, not pair creation, but it should be the Hawking temperature.
Yes, we want to recover the.
Yeah.
I think it's a value of a temperature measured at infinity.
Yeah, at infinity. It's not Hawking temperature, it's equal to that.
Yeah.
Oh, we want to describe.
If I take a hot object sitting there and I measure its temperature very, very far away at infinity, it's 0.
Yeah.
Right? Hawking's temperature is very particular to actually having a horizon. So I don't know what this means.
Oh, if you look at.
I think what he's saying is fix the mass. He's taking Schwarzschild, fix the mass, take the value of the Hawking temperature for that black hole that you would measure at infinity.
Okay.
And then put your surface there and cook up your model such that the local temperature of that surface is blue shifted in exactly the right way so as to produce the same temperature. I think that
Giving me the scale of the blue shift.
yeah, that's its equation. The first twiddle, I think, is that equation.
Okay.
Sorry. Okay. Okay. If you want to recover this same amount of energy of the emission at infinity, then the particle near the surface has very large energy. So this amount of energy. Another thing is, if you want this particle emitted from this surface be able to go to the infinity, so it has to move in a very small angle called escape angle. So you can see this escape angle is very small. It decreases with s. When s is very small, so this is a very narrow angle here. Okay. Now you due to this escape angle, you can see most of the radiation. If you want to recover the Hawking temperature at infinity and also the emission rate, but you know most of the particle will not go to infinity. It will go away from the horizon and then falling back to the this surface again. So most of the particle will stay in the region but not go to infinity. So you can expect they will form a hot gas near this surface. Oh, because this local energy is very high, so it's very hot gas. Oh, we do a simple estimation later, but here I will not show you this. So now let's let's put a hot gas near this ECO surface, and there's some facts of this hot gas. So the local temperature is 1/s. S is the, if you look at any proper distance away from the to the horizon. So S is the proper distance. So the temperature become very large when you go close to the horizon, at the surface. And another thing is the separation between two particles is also S, and the wavelength is also S. Oh, yes, yeah.
What I'm thinking here is that you have a certain temperature. The Wien's law tells us that the dominant frequency or dominant wavelength is the same order of the temperature, but the separation of particles is the density of particles. That was the only thing that made me wonder. Is it really also the same?
Yes, yes.
Okay.
So you can see the distance is at order of the wavelength, so they are not that coherent. Okay. So now let's look at some infalling probes. Let's first look at high energy infalling particles. The energy of this infalling particle at infinity is larger than the Hawking temperature. So when the particle moves close to the that hot gas, it will get energy will get blue shifted. So the local energy of this local wavelengths of this infalling particle is much less than the S, the separation of the hot gas particles. So the infalling particle will only see one of the particle, and Samir and Turden studied this, and Sean and Samir also studied this. So the result is there are very small probability of backscattering due to two reasons. One is at high energy, the cross section is very small, and the other is due to this escape angle, because the scattering between this particle and the infalling wave is not exactly going back to infinity. So you have the escape angle problem. Most of them the reflected wave will go away from horizon and then falling back to the horizon. The situation is quite different for low energy infalling wave. For low energy things, the wavelength is the local wavelengths of the infalling particle is much larger than the separation of the distance between two nearby particles. So you will get lots of particles in one wavelength. This is half wavelength. So this is usually called coherent scattering. So the amplitude grows with the number inside this wavelength, so you get an enhancement factor. Another important thing is because now the wavelength is longer than the separation. So if you look at scattering from each of them, so the phase will get cancelled in all the other direction. Only the one going straight away from the horizon is the most possible one. Okay, so there's no escape angle problem if the wavelength is large enough. So for the electromagnetic wave, is studied in Chuan and offshore this paper, and we study the gravitational case, wave case. So let's estimate the reflection for a gravitational wave. So we do a detailed computation, but here I just use dimensional analysis. So let's consider this hot gas to be a thin shell of fluid, so it responds to the gravitational wave very quickly. And the pressure is at the order of the density set by the the scale S. So now let's look at a very long infalling wave. So we know that so this look at the amplitude of the infalling amplitude divided by the outgoing the amplitude and divided by infalling amplitude. It's a dimensionless thing. So it's proportional to the gravitational coupling G, and also proportional to the mass per unit area. So dimension 3. So dimension -2, we need dimension -1. So it's the wavelength of the infalling particle. So this is an estimation in the flat spacetime. So now let's apply this to black hole. So for the black hole, the mass per unit area is, let's call this is the yellow one is the hot gas, and the gray one is the ECO surface. So the density of the mass per unit area is m prime. So we got the total mass of the hot gas is m prime over r squared. The m prime is bounded by the total mass of the black hole times the blue shift factor. So we get this result. And the wavelengths, if the infalling wavelength is at order of the Hawking temperature, so at the near the S shell is this value. So if you put everything here, you will see it's an order 1 number. So actually, you can get order 1 reflection in this model, and it should be true for any model that if you find enough microstates, and you will generate this Hawking radiation, and they form a hot gas, and then the wave will be reflected by the hot gas.
For this calculation together, this is just a hot plasma and surrounding a black hole.
Oh, the plasma cannot carry all the entropy.
Right.
The compact object has all the entropy.
Yep.
But because you want to recover this Hawking radiation, the emission from the hot gas will generate a shell around the microstates.
Okay.
But itself doesn't carry that much entropy.
Everything you've done so far looks just like a hot plasma with the obvious density around a black hole. But you made a remark a moment ago about the counting if you have the number of microstates. Where was that an essential part of the calculation?
Oh, I see. So if you have enough microstates, so the surface must be very rough because we have large entropy.
The surface must be very what?
Oh, very rough.
Rough.
Yeah. So there's lots of fluctuation you can think of. So it's not that smooth. So the emission from that surface should be isotropic. Because it's almost isotropic, so most of the particle will not go to infinity and stay in the region.
Good.
And become a hot gas. So if you have a reasonable model of microstates, you must have this hot gas around the microstates for finite temperature black hole. Okay, any questions? Oh, yes. Oh, actually, I will mention this later. So in this estimation, because the coupling is G.
Yeah, the only coupling is G.
Yes.
So, okay.
And but it's quite different for the electromagnetic wave.
Yeah, that's why I asked the question.
Oh, I will discuss this later.
Okay,
Oh,
thank you.
for the question. Okay, here's the short summary. So if we can find all the microstate and try to build a finite temperature model for the fuzzball, there must be real particles emitted directly from the surface, and they will form a hot gas or hot plasma around this compact object. And the low energy infalling wave will be reflected by this compact object. The surface of this plasma is very smooth, like a mirror, so you can get order one reflection. If it's not mirror, it's very rough. For example, for high energy, then you will not get reflection. Okay, so we build this model.
I'm willing to, go along with this toy model, right? But of course, this is a toy model for what we expect really to be the case, right? Because we don't really expect there to be a well-defined hard surface in a real fuzzball, for example, right? It's more like once you get to this horizon area, instead of a horizon, you have structure and all kinds of stuff going on. And so, I mean, I guess my worry in the real world, right, would be that there's not really going to be a surface. There's not really going to be a hot plasma, because the hot, whatever particles come out of this complicated structure will sort of, as you say, they will, come back to the structure, but then the structure eats it up again, and it's this very complicated, always in motion kind of stuff going around. And so it's hard to say, or it will be, it's only an approximation to say there's a surface and there's a plasma, right? It's going to be all kinds of stuff going on.
I think the question is, where's the separation between the surface and the plasma?
Yeah, I mean, you don't really expect there to be a hard separation.
There is a corona sphere around the sun.
Yeah.
Hot gas,
Sure.
not the
Yeah.
anything that
I mean, in black holes, I'd say this is sort of a different thing, right? I mean, I don't know if this is what we should expect, but it's a bit of an assumption, I would say. Do you want? Yeah.
But I think Tim's trying to build something that's reflective.
I agree. So as a model, I'm fine with going along with it. I just want to be. I guess I want to ask, like, how much are the details of what follows, depending on the fact that you have this hard cutoff surface and a plasma next to it, and that there's no mixing or whatever.
Oh yeah, I think this relative Yiming's question. If the I will talk about this later.
Okay.
But here we just assume it's most of fuzzball are very compact.
Okay.
So the one with large fluctuation is not the most generic one.
Okay.
So just assume it's very, very compact.
All right. So I'll ask for it.
If there are clear hierarchy in the model, then you can find a clear separation.
Just to add a simple comment to that. So you know that if it really was a black hole, and if you manage somehow to go fairly close to the horizon and hover above it, you would measure the en route temperature, which is a blue shifted version of the Hawking temperature from infinity to whatever place you manage to hover. So this model is basically extrapolating that into the very near horizon region, where, so I think the expectation of this kind of plasma should be generic for such models of compact objects. So wherever you push some edge of whatever effective surface you want to build more generically, whenever you're outside of that, you should have this kind of plasma of radiation.
Disagree, right? The details of it might be important.
Yeah, so I guess he has some wiggle room because of this order one reflection coefficient, which so you're saying basically in your model there's no parameter that makes that very large or small, but he can tune, you could have 2% reflection or 98% reflection within this order one.
Yeah, or maybe I think, let me just discuss this here. So in our computation, we just find order one. So there's another order one that can go inside of the surface, this plasma, and touch the structure of the ECO surface. So in this model, for the gravitational wave, there's no clear separation between the for the between the ECO surface and the plasma. They are mixed at the Planck scale. We assume even at Planck scale. But if you look at the electromagnetic infalling wave, then because now the reflection is caused by the coupling is very strong. So, and the reflection is at a place very far away from the ECO surface. It's at the place of but you can create E plus E minus. So it's not Planck distance away from the horizon, but 1 over ME. ME is the mass of electron. This place, you can get a large reflection. So the wave function will not touch the surface here. So you have a clear definition of where is the plasma and where is the ECO surface. But for a gravitational wave, it's not that clear. But I think the idea is if you want to make this surface very compact, you have to form this plasma. If most of the fuzzballs are very diffused, then the plasma is not good description. Okay. Oh, we just try to understand this without knowing the fuzzballs. Another interesting is if you look at the electromagnetic wave, it won't touch any of the fuzzball surface. So it's like a screening effect of this plasma. So you will not, by using the photons, you cannot see this effect from outside. Okay, now let's look at the formation of a new trap surface. So the idea is in a real situation, there's not only one infalling graviton, but many of them. So the energy is large enough. So if we can see actually the infalling energy is at the order of the mass of the whole, same order. So let's estimate the size of the new trap surface if we put this this energy there. So it's this amount. So for gravitational wave, the energy, infalling energy, is at order of the mass of the whole. So the trap surface is at distance r away from the horizon.
We're all about converging geodesics. So what sense is this a trap surface?
Oh, it's if you take the classical general relativity, that's the new horizon.
No, I understand, but usually when you say I've got a trap surface or closed trap surface, you start proving theorems about geodesics converging in both directions. So why is this a trap surface, or is this some other notion of trap that isn't the usual one?
Oh, that's the usual horizon. Maybe we should say
Okay.
Formation of a new horizon.
Okay, so I want to see something about convergence of geodesics.
I think they're saying that if we have extra mass, where it would be structured radius.
Oh, okay, is that it? Okay.
Some number of mass where the new structure radius.
Okay.
Yeah. Yeah, if you put them
Good.
more.
Okay, then that's fine. Okay.
Yeah, it's that simple. Now, if you look at the local wavelengths of this ingoing gravitational wave, it's very short compared to the size of the black hole. Also, the local wavelength is as shell if you touch the surface of the hot gas, but it's much less than the size of the horizon. So if you take the classical general relativity, infalling waves will be trapped inside by the new horizon and cannot be reflected to infinity. But is this consistent with the reflecting boundary condition you put at the ECO surface? Because we want a compact object to replace the black hole horizon. So should we use that intuition? So we want to ask the question: what happens when a new horizon forms?
What's the limit? So this was for dumping a gravitational wave, which was comparable to the mass of the original
Yes.
black hole. Suppose I crank that down so that it's some small parameter times the mass.
Yeah,
when do you get?
Then
just remind us what the lambda. There's some ratio here. What's so you have some lambda local, which is
lambda local will be the same, but
what was the order of magnitude of
the trap surface will become smaller.
Exactly.
Yeah.
So can you,
Oh,
where's the limit of this, whether you're barely forming the trap surface if you have less energy that you're dumping on
oh,
the
it's
black hole?
just one. If you take the surface at the Planck distance away from the horizon, then it's just one Hawking quantum, just one graviton.
Okay, so you're saying anything more than a very weak Hawking. So if you're dumping in some very weak flux like the Hawking flux, that's the borderline case, and anything more than that.
Yeah, would be
So
a
it
problem.
doesn't have to be an order one.
But in the real situation, if you want to detect this wave, it must at order of the black hole. Oh, from the gravitational detector.
Oh, you're
Yeah.
That's the question.
Sorry? Yeah, still trying to follow this. Where does the formula for S trapped come from? The square root of M, square root of E. Why that? I mean, I was expecting, based on Bogdan's remark, that this would just be the delta M associated with the shell that you've added of this plasma. So why isn't it just linearly proportional to the delta M? And 2G delta M was.
Oh, it's the proper distance.
Sorry?
This is the proper distance.
Proper distance. Oh,
not the coordinate distance.
Thank you. That's good. Okay, so there's a square root involved and you expand the square root. Excellent. Okay. Now, why is the energy in this plasma of order the mass? That seems outrageously large.
So we have the main part of the gravitational wave of this profile, this template. If you want to observe these signals, it must be at the same order. Otherwise, it's too weak to see.
It's too
weak to see the signal.
I thought it was reflected, so
It's
whatever
reflected.
you send in will get sent back out again. So,
let me put this. So there are two reasons why this should be at this order. The first one is because the main gravitational wave, the main part of the gravitational wave, is at this order, and the outgoing part, and we observe and we find this pattern, and also ingoing part, and this ingoing part is actually this infalling part, and generated, if it's possible, generate a reflection.
okay. But it's
So in a real situation.
Sorry, I thought the whole idea was that there was some plasma outside the horizon, and at that point, I was supposed to be thinking of that as a rather small fraction of the black hole mass. Now you're telling me it's of order of the black hole mass. That sounds like the tail's wagging the dog. It sounds like there's too much stuff.
I think I'm getting it. So in real situations, we observe mergers of black holes, which are 10 to 20 solar masses, and the energy in the gravitational wave of the initial burst is 1 or 2 solar masses.
Yes.
So it might be a factor of 10% or 5%.
Yeah.
Okay.
This information. I thought this was just thing settles.
The picture I was supposed to have is that I have a black hole and it settles down to its mature ancient life and it just starts forming a plasma that's in equilibrium with the environment. And I would have thought that plasma only involved a tiny fraction of the mass. Why would it involve a big fraction of the mass?
The E is the energy in the gravitational wave we're dumping on the horizon because it's about to merge, or it's in the process of merging with another black hole. Echoes and mergers is the setup.
All about mergers of black holes? Oh, okay.
Yeah.
No, I just want to.
Oh, I think I need to explain this.
Okay.
So,
it's the echoes of mergers. I'm sorry. Okay, good.
yeah,
Very
if you
happy.
consider coalescence of two black holes,
I'm being slow this morning.
and you will generate, this is not, but suppose you have this part is the main gravitational wave pattern, and then some of them will go inside and generate these echoes after the rain down region. So in this case, the mass of the gravitational wave coming into the black hole is at order of mass. Okay. So let's consider what happens when a new horizon forms. So this is a picture to understand in this case. So let's consider an infalling shell, and before the shell moving into the horizon, you will have some virtual fuzzballs. So these are extended objects And if you, okay, so they are virtual because we do not have enough energy inside. If the shell going inside into its own horizon, then all the light cone point inward. So due to the causality, the structure must be compressed. So if you compress this structure, you give some energy to the microstates or the fuzzballs, and then they become real. If you after several crossing times, then you will generate this ensemble of microstates. So this mechanism is called vacuum hypothesis by Samir. And so the idea is we need to form the closed trap surface first, and then because of the causality, this structure will compress the virtual fuzzballs and make it real and generate the microstate structures.
Saying that a closed trap surface forms and no echo ever comes out, right? So
Yes.
your conclusion is independent of vector hypothesis.
Yeah.
Okay.
Oh, but we just try to understand this in fuzzball.
Yeah, I just want to disentangle the two things. So many people may not swallow the vector hypothesis, but if you show there's a closed trap surface in this process, then
Yeah, it's more general than in fuzzballs. And the very important thing here is, if you want to get this reflection, we need this plasma, the hot plasma. But it takes a while to generate this plasma. So after a few crossing time, so you will get fuzzballs and radiate from this surface and generate the plasma. So you cannot generate the reflecting boundary condition suddenly. So if this particle of this incoming wave moving inside the horizon, at this time, it won't reflect the wave. But if you wait several crossing time, then you will generate hot plasma. And then if you drop another wave, then it will be reflected. But this wave will go inside the horizon and without much reflection. Okay, so we are not be able to see these echoes. So there are some discussions. So the model we consider is finite temperature. So the picture is quite different for microstate with zero temperature. So for zero temperature, you will not have this hot gas. So just go through and touch the cap and go back. So the picture is quite different. And for the gravitational wave, there's no clear separation between the surface and the plasma. But for the electromagnetic wave, it will be reflected far away from the surface. And so there's a clear separation. So they can be reflected very easily. So if you have a lab that can create a very small black hole, and you want to test it, if this has some reflecting boundary condition, some microstates, it's better to use the electromagnetic wave. So if you put some electromagnetic wave, it will be reflected, and it can be a little bit stronger than gravitational wave because the distance away from the horizon is large. So if you form trap surface inside of this region, it's fine. Okay. So another very important thing is the reflecting boundary condition takes a while, several crossing times to generate after the formation of new trap surface. If you try to do a simulation and put some boundary condition, but assume this reflecting boundary condition can be generated extremely quick, so you can get some reflection. But the problem is it cannot become it's not that sensible in fuzzball understanding. So it takes some time to generate this hot gas and reflect the wave. Another thing is these echoes are very simple operators from far away. So if you look at the classical black hole or the computation in island, you should not be able to see them. So if you can do a real experiment, you can distinguish the two kind of proposal. I'm not quite sure I understand that correctly, but this is a very simple operator. Okay, so that's all. Do you have any questions?
Okay, so it still sounds to me like you're setting up a very particular kind of model, right? So let's forget about, what we know from fuzzballs for a second. It sounds like you're setting up a model where, okay, somehow we've managed to create, right? There's some formation channel which has created not a black hole, but something that is very, very compact, right? Has a surface very, very close to the black hole horizon. Okay, so that's one. And then you say that, okay, actually this forms, right? We do know something about the formation of this kind of thing. First, you get a trapped surface, then it turns into this kind of reflecting non-trapped surface, right? So there's a chain of assumptions of like how this works.
Oh yeah,
in
I
there.
can make comments on these assumptions.
Right.
I think I think we expect if we can find, for example, if another theory to describe the microstate, and we guess it's very compact, the microstate should be very compact. So
I
think that's
agree.
a reasonable assumption.
Yeah.
Another thing is about the formation of a new horizon, and
Yes.
because we don't want the fuzzball very, very different from a generic one, very, very different from black hole. So one reason, I think maybe I can add another. This is not a very special property of this model, but from the causality. The reason is, for example, if you have a shell collapsing into a black hole, before they touch, so because they are moving at the speed of light, there's no causal connection between each part of the shell. So
Okay.
you cannot generate from the interaction between different parts of the shell to generate some microstate structure. It's impossible because of the causality.
It's impossible if everything is strictly local, right?
Yeah.
Yeah.
If there's
So
yeah.
this is big assumption, I would say, right there.
But it's a smooth it's very smooth. The space-time is very smooth. It's local, so it must be normal physics, low energy effect. So,
Okay, I mean, but this is maybe a point of debate. I mean, okay, I don't disagree, right? But this is, we know there's non-localities in gravity, right? And who's to say, okay, a lot of people would say maybe that there are non-localities that would be small for any classical observer, but they have a large effect in sort of let's say the microscopics of the theory, right? And so,
but in this case, this is not a very complicated object measurement, so you won't. I don't think you will see this small effect accumulated into something like that. So this is, I think, largely constrained by the causality. So if you want to form this microstate, you have to first form the trapped surface, and the trapped surface compress the virtual one. It can be any other theory, but compress the virtual one and make it real. You cannot talk to each other and make it possible, the microstate. So it's quite general.
right.
Yeah.
I mean, I don't disagree with the conclusions once the premises have been set up. So yeah.
I just had a simple question. So you said that this reflecting surface, the hot plasma, the thin shell of hot plasma outside, forms in a few crossing times. Do you know how much time does it take for the wave to travel from the photon surface back to the echo, to the extremely compact object?
It's
on the very
very
first
large
slide.
number. Yeah.
So the
number.
distance from the photon surface to back to your echo, so to get reflected back, how much time does that take?
For solar mass holes is 50 million seconds.
And in crossing time, sorry,
Crossing
how
time,
how does that
small.
compare to the time it takes to form the
Crossing time?
The reflecting surface.
Oh, from the surface to the photon sphere.
Yes. So how much time does it take for the wave to travel between those two surfaces compared to the time it takes to form the reflecting surface?
This value. Oh, the same number. So the equal separation is the time from the surface to the photon sphere. The same thing.
Okay. So the order of the crossing time.
Yeah, so the ratio between this and the crossing time is this number is very large. Yeah, log E. Yeah, it depends on where you put the surface, but it's a very large number if you make the thing very compact.
So the reflecting surface will form before any of the reflected of the echoes come back.
Okay, say again.
So you have this formation process and you form this whatever object, and then it takes some time until the actual reflecting surface outside of the form.
Yeah.
So, and I'm asking, does this form before the first reflected gravitation away from the photon sphere at the right path?
Oh, you mean from a distant, far away observer? It doesn't. It's not. I know the answer, but I don't.
Good question about your question.
Yeah.
Are you asking, so with the initial wave goes in,
Yeah.
and then there's a first reflected wave, which is the tracing back of the first echo on the way out. Are you asking whether that guy gets out before its own closed trap surface forms?
Kind of. I'm asking, so you form the object. I'm asking, so you form your object, and then it takes some time for that object to form this reflecting surface of hot plasma or gas. And I'm asking whether the wave that we hope will hit the photon sphere and come back, the burst of gravitational energy from the formation, whether that will get reflected back from the photon surface and come back to the echo before the actual reflecting surface will form at the echo.
Oh, I kind of understand. So, for example, if you generate put a very small wavelength, small energy, you generate some very hot gas very close to the previous one.
Mm-hmm.
Okay, and it takes m to do that. But the time you go outside and go back is m times log epsilon. So it's much longer.
Oh, it's much longer. Okay, good. Perfect.
Oh, but it will get trapped first, so it cannot go outside and go inside to get reflection. Yeah.
Hi, I just had two clarifying questions. So one, if I'm understanding correctly, at the end of the day in your explanation of this mechanism of the hot plasma forming a reflecting surface, you didn't actually need to assume anything about the reflectivity of the ECO surface itself. Is that right? Well, besides the fact that it emits radiation isotopically?
Yes, yeah, I think
so you didn't, yeah, so my question, I guess, is did you assume anything about the reflectivity of the ECO surface itself?
Oh, yes, let me. So the idea
in this analysis?
There's a no clear separation for low energy gravitational wave between the ECO surface and the plasma. So some part of the wave function will touch the ECO surface.
Okay.
But we know because the energy, one argument is if it's highly absorptive, even for low energy, it can be reflected due to the plasma. Or another, but it's also possible it can reflect the gravitational wave because the energy is much lower than the energy gap of that system. So it can be reflecting boundary condition there. But the conclusion is doesn't matter. Okay. The plasma can reflect enough.
Okay. And my other question was just, are you assuming that this epsilon deviation of the ECO surface position from the Schwarzschild radius is like, what are you assuming for the scale of that? Because that seems relevant for the question earlier of kind of what's the limiting case? Like if we take the energy of the gravitational radiation to be an extremely small fraction of the mass, you were saying that like you would still have a new trapped surface outside of the ECO surface, but whether that's true seems contingent on how big the ECO, it's sort of a trivial point, but if the ECO surface was a little bit farther out from the original Schwarzschild radius, then the new trapped surface might still be inside the ECO surface. So is that just an unrealistic possibility, or is there any chance that could be the way things pan out here?
I think the usual guess is a Planck distance away from the horizon.
Okay.
But because the new trapped surface is very large, it can be any any size between 0 and R. So there's a large enough room you can make assumption of this.
Okay, thanks.
So if the ECO is very large, so you won't get large reflection for the gravitational wave. But if you try to put some boundary condition here, you will still have this problem, the new Chapter surface. The main result of our argument is we should consider new Chapter surface. The model is just try to show it's possible.
But just so you're assuming though that the original ECO surface is like some epsilon, which is like a
any parameter.
order. What's that?
If it is smaller than the size of R, then the mass, the horizon size, then that's fine. Much smaller, then that's fine.
Okay.
It can be Planck mass or other scale, energy scale. That's fine.
Maybe following up. So you're assuming it's definitely small than, like, I mean, even MRES is not going to save this, right? Like where you have a really large black hole and a very small thing that you throw into it. And then, right, I guess that's what Peter was asking. Like, can you tune the stuff
yes.
that you're throwing in so that this doesn't work and that your trapped
Yes,
surface is.
Yeah, lots of, but in a real situation, the mass of an infalling thing is order of m. So you want to just consider the experiment we can do it in a near future.
Well, if you mean order m, I mean it can be like a factor of 10 to the 6, 10 to the 7 difference, right?
So yes, we just assume the it's not order of the ECO surface is not order of m, but another parameter can make it very small.
Yeah.
I think it's reasonable. I think most of fuzzball will not be that large if you can find all of them. The large one looks like a star, not a fuzzball.
Right. Can I ask another question? So you mentioned Afshordi at some point. So his arguments, which I'm not super familiar with, but he has an argument where it's exactly also this Hawking radiation kind of gas that will produce and give measurable echoes. Like he calls it some kind of resonance or something. Can you comment like how is this? Because this seems like completely different. Like it seems like the same starting point, right? You have echo ECOs with Hawking radiation, and then a completely different conclusion, right? You conclude no echoes, and he concludes stimulated emission.
I think that there are lots of papers to study echoes, but the idea is to put the reflecting boundary condition all the time.
Mm-hmm.
Even there's some simulation to do that, and you will see some echoes. But the only difference is here we argue that the reflecting boundary condition cannot be generated very soon. It takes several crossing time. Then you have to consider trapped surface. So the new thing here, the conceptual new thing here is a new trapped surface. We have to consider this back reaction. They only consider the perturbation. But the echo is not a perturbation. It's very large amplitude thing.
So you're saying what Afshordi does is he's considering also this sort of gas of Hawking radiation stuff.
Yes, but there is a perturbative computation.
Good, and he doesn't look at back reaction, basically. He ignores that, and therefore he gets stimulated echoes, but you say no, they're going to be trapped by this back reaction.
Yes. Okay. So we have to consider this simple idea. There's some back reaction.
Question.
Just going to make a comment, really. In the early days of the Clinton campaign and in the US presidential election, they used to put on the wall of the campaign office, Carville put this thing, "It's the economy, stupid," to remind everybody that that's the only thing that matters. And I think another nice illustration that probably Samir's maxim should be, "It's the back reaction, stupid."
Okay, thanks, Nick. Any more comments or questions? Okay, I don't see any. So let's thank Ben again for a nice talk.
Thank you.
And we'll have